Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Alright, step on inside. You might have already been inside as we are doing back-to-back videos. You're going to see this outfit, this getup, and this game back here a couple times if you just came off arithmetic sequences. And I hope you at least came off that video a little bit if this is your first time learning geometric sequences, because that is when I introduced what explicit formula meant, what recursive formula meant, different formulas for geometric sequence, but they are very important as far as how sequences exist, or what sequences mean when you use them, and the explicit and recursive rules. So I'm going to link for you the arithmetic sequences thing at the bottom down here. In about the first 10 minutes of that video, I barely even do a problem in the first 10 minutes of that video other than talking about what those rules mean, what the sequences do. So if you don't know what they mean, you might be a little lost on this one. If you do know what they mean, step on inside. We are going to be looking at geometric sequences and taking care of business here with brand new formulas. Prior to that though, and I did mention this in the arithmetic sequences video, we are going to look at some things that do involve arithmetic stuff. Now that geometric is the new thing to cover, arithmetic and geometric can kind of we can work with both. So we're going to determine in numbers 1 through 4 whether each sequence is arithmetic, geometric, or neither. You can have sequences that can do other patterns. Some of them you might not know what they do. Some of them are more obvious than others, what have you. And at the end of this, by the way, we're going to talk about arithmetic mean and geometric mean. So arithmetic will come up again. Now, state if it's arithmetic, geometric, or neither. Now, an arithmetic sequence, as I stated in the previous video, features a common difference that each value is separated by the addition or subtraction of the same number over and over. Geometric sequence, on the other hand, features what's called a common ratio. Some things say common multiplier, which might make more sense with regard to what it is that we're doing. From one value to the next, you are multiplying by the same thing over and over. And if it's neither a common difference nor a common ratio, then it is neither an arithmetic nor geometric sequence. Now, some of these are more obvious to do than others, but when you're dealing with fractions, maybe not so much. It depends on if you're really savvy as far as realizing what you're potentially multiplying by or adding to. If you're not, I do want to show you some fronts on that. However, maybe you do recognize it all the same. Like this first one here. What you can tell on number 1 here is that -5 is a constant on top in a numerator where the denominator seems to be changing. That's not something that you'd often see in an arithmetic sequence because you can't be adding something over and over and not change that top. Right? It seems like this is something that could occur in a geometric sequence, though, because you could be multiplying by something over and over to make this happen. Now, remember, -5 is also -5 over 1. So really what we're looking at here is as the -5 stays the same on top, and we're essentially multiplying by 1 on top here, assuming this is geometric, just to try it, what are we multiplying by on bottom if there's a common pattern involved? So if there's times 1 on top, on bottom, looks like we're multiplying by 4 there. 4 times 1 is 16. Oh, 4. Is that a times 4? You betcha. And I sure hope they're not doing, yeah, 1/4. So it looks like the common ratio here is 1/4, which makes this a geometric sequence. Now that's a little bit by happenstance of I know how those numbers work, right? I'm very aware of that. You might not necessarily be. So when it comes to you doing a test, what you might have to do is say, if I don't know what I'm multiplying by from one number to the next, and I did something very similar to this for arithmetic sequences. If I don't know what I'm multiplying by from -5 to some common ratio to get -5/4, what I got to do is I got to solve for r. I got to divide both sides by -5 or multiply by -1/5 in this case. When you divide by a fraction, when you divide by a number, you multiply by its reciprocal. So a fraction like 5 over 1, -5 over 1 multiplies by its reciprocal there. -5 over -5 is +1, and then you get 1/4 right there. R is 1/4. So, it points back to what we're doing there. So like a common difference, you subtract one number from the one before it to figure out that number. And I'd have to do this over and over, by the way, guys. This was just 1/4 once. What if I do it again? What is -5/16 divided by -5/4? One number divided by the one before it. Well, that's -5/16 times -4/5. Now, a negative times a negative is a positive. And then -5 over -5 is gone, you're left with 4/16. Well, that is 1/4 as a reduction. So you'd have to kind of check over and over to make sure of it. I don't know if they're going to trick you down the line If two of them work out, definitely make sure that it's still working. But this one does have common ratio of 1/4. This one is a geometric sequence. That can be the test that's involved. And again, I kind of just knew by math logic that one wouldn't be arithmetic. Maybe that's not something you notice immediately. But you check for common difference and there wouldn't be one. All right, check out number 2. One that is significantly less obvious here. -1/3, +7/6, +8/3, 25/6, and 17/3. Make no mistake, these numbers are ascending. Now, I do want to mention one thing that I know is actually not for sure, and it's only because this one was negative here. It's not going to be a geometric sequence. Now, we're going to notice these when we start doing more down the line here, but in a geometric sequence, as you notice, all these signs were the same, all negatives here, because we were multiplying by a positive number. They could all be positive as well, and if we multiply them all, then they're a positive number as well. Then they'd all be positive. But here we went from a negative to a positive. Now, how is it possible to multiply this by a negative number by some value and get a positive? You'd have to be multiplying by a negative number. So if we're looking for a common ratio, that means that whatever we'd have to multiply r by right here to get 7/6, this r would have had to have been negative. Well, to have a common ratio, that means this would have to be the same r, which means this would also have to be a negative number. A positive times a negative should give me a negative here. This isn't negative. So if this isn't negative, I can say off the bat through that number logic, or through number sense, this is not going to have a common ratio. This is definitely not a geometric sequence. Even if this was positive, even if you would multiply by something to increase this, and it very well may be the case that it is, but the very fact that it does change sign right there, and we luck out, means I don't even need to test for geometric sequence. It can't be one. Is it an arithmetic sequence? I don't know. Listen, I don't know off the bat whether it is or is not. These numbers are not plainly obvious to me. It does look like they're increasing though. -1/3, 7/6 is a little more than 1, 8/3 is 2 2/3. This is 4 1/4. This is 5 2/3. Are we increasing by? We're increasing for sure. Is it arithmetic? It very well could be. How do you check? You will check by testing the difference between all numbers. We got to see what the difference is between 7/6 and -1/3. And notice when I said difference, I subtracted, even though I'm subtracting a negative. That's 7/6 plus 1/3. Oh, let's see. Common denominator, 2/2. So plus 2/6, which is 9/6, and reduces to 3/2. Let's try it again with 8/3 minus 7/6. 1 minus the 1 before it. Now listen, if this doesn't have the same difference as the others, I don't need to test anymore. A single test of two different differences means there won't be a common difference. And if there's not a common difference, then we're good. So let's check this one out. This would be times 2/2 right here, and we get 16/6 minus 7/6. Well, hey, that is also 9/6, so we get 3/2 again. Hey, this very well could be an arithmetic sequence. We got to check again. We got to see if we still get 3/2. You got to be sure all the way down the line, especially if it's not plainly obvious. And it's not plainly obvious to me. Here we go. 25/6 minus 8/3. Times these by 2, okay? So that's 25/6 minus 16/6. That's also 9/6, which is 3/2. Last one, 17/3. Sorry about the room. 17/3 minus 25/6. 17 is 34, so 34/6 minus 25/6 is 9/6, which is 3/2. So yes, we have a common difference of 3/2. That makes this an arithmetic sequence. Arithmetic. So it is an arithmetic sequence, and that is the only certainty to do with this. Now, if the numbers were plain as day, +2, +2, +2, you don't have to show all the subtraction. You were showing the subtraction not for your instructor or anything like that, for your evaluator. This was for yourself. I didn't know it was that. I knew it wasn't geometric, but there's that. All right, number 3. Here's perhaps an obvious one for us. I'm going from 1/2 to 1/2. That means I'm either adding 0 or multiplying by 1. Am I adding 0 again or multiplying by 1 again? No, because otherwise it would stay as 1/2. I think it's safe to say, without any math to show, that this is neither arithmetic nor geometric. That's not to say that after that 1/2 that this isn't maybe doing something that's of an arithmetic or geometric pattern, but it only takes one to break that common difference or common ratio. Is it doing something? I don't know. Times 3 over 4 times, no, because that'd be 9 over 32. So it's not geometric. I don't know if it's arithmetic, but I'm going to say. It was. From here to here, it does have an arithmetic pattern. I think you're subtracting 1/8 here. 1/2 minus, because that'd be 4/8, minus 1/8 is 3/8. And then 3/8 minus 1/8 is 2/8, which would be a quarter. So those ones actually fall, just those three follow an arithmetic sequence pattern. Nothing after, nothing before. But those three do. So I guess there was something to it that they wanted to point out. I don't know. Anyway, neither arithmetic nor geometric. Sorry, guys. All right. Oh, so neither. Now, when it comes to neither, you need to show that it's doing something different. So I could say, hey, I know it's not geometric because this is times 1, and then it's times 3/4. So that's not geometric. And then for arithmetic, you could say it's plus 0 and then plus, or what was it, minus 1/8. Those are good examples of showing that it's neither. It's kind of like, I don't want to bring that up, but it's kind of like proving that something's sometimes true. You ever done always, sometimes, never? To prove that something is sometimes true, don't just guess it. You got to show that it's never always true and never true. Right? So same thing here. To prove that it's neither, you got to show that it's neither geometric nor arithmetic. Okay, last one, number 4. -48, -12, -3. When you look at these, you say to yourself, it looks like we're dividing by 4, and that's a good start for this one, dividing by 4. Now, I'll have you know that dividing by 4 is not how we state a common ratio. That's not to say common ratios can't include division as a principle for whether you have a geometric sequence. But we wouldn't say divided by 4. We should be saying times 1/4. But I understand if you need to say divided by 4 to start with to make sense of this. Even this next one, divided by 4 there. But is -3/4 divided by 4 -3/16? That's where you might want to say times 1/4 there. And yeah, -3 times 1 is -3. 4 times 4 is 16. It is that. So your common ratio is 1/4. That's the same thing as dividing by 4, remember? That does make this thing geometric. And I just saw that as an avenue. Clearly it's not arithmetic because you're not subtracting, or adding, I should say, the same thing over and over. And if you recognize something you can get out of it like this, I never used division to determine that it was 1/4, but you could have done -3 over -12 and gotten 1/4. For instance, that will give you geometric sequence. Okay, that one was a little bit longer to do, to talk about, but I hope you're understanding the idea of common ratio, because now we're going to get into how geometric sequences actually work. And what they do is, as you've seen, you multiply by something over and over again. Like for this list of 2, 4, 8, 16, 32. You're doubling your values, times 2, times 2, times 2. And unlike an arithmetic sequence where you add or subtract the same number over and over, when you add or subtract, your explicit formula shows it through multiplication. If I add something over and over a certain number of times, then I can multiply that number by how many times I'm going to do it. But in the case of multiplying something over and over, you express that through exponentiation right here. If I want to multiply by 2 10 times, that's the same as 2 to the 10th power. So a geometric sequence has an explicit rule that is expressed using exponentiation and, of course, a common ratio. To find the value, and this is stuff from my arithmetic sequence stuff before, as far as understanding these, the words I'm saying. To find the value of any term n, you start from your first term, some a sub 1, and we're going to multiply by that common ratio n minus 1 times. This is the explicit rule for a geometric sequence. There is a version that you could do that is a sub n equals the value of the theoretical term 0 times r to the n power. I'm not going to use that. It could appear from a problem, but I'm not going to use it, so you're good. So you remember the whole n minus 1 times thing. I think we spoke on that several times before with arithmetic sequences, so I hope that makes a little bit of sense why it is specifically n minus 1, starting from the first term. Okay, here's what we're going to do. Given the explicit formula for a geometric sequence, find the common ratio, the first 5 terms, the 8th term, and the recursive formula. So we don't have to do it in that order, but given the formula that you have and the understanding of how common ratios work, multiplied by same number over and over a certain number of times, 2 appears to be that common ratio. R is 2, as it matches right there. That means we are doubling something over and over, starting from negative 3. Now they say list the first 5 terms. If negative 3 is the first term, our a sub 1, then I can start writing things out. Negative 3. And although I could tell you we're doubling, let me revisit how you could use this formula to work some things out and make sure you know how exponents work. So if I wanted to find a sub 2, I would take negative 3 and multiply by 2. 2 minus 1 times, that's 1 time. Multiply by 2 once. Negative 3 times 2 is negative 6. And that's the same thing as doubling, negative 3. A sub 3, one more time here, is negative 3 times 2 squared. Again, 3 minus 1. 2 squared is 4, so you have to do order of operations there. So negative 3 times 4 is negative 12, which again is doubling the negative 6. Now, I didn't do it for a sub 1, but that would have been negative 3 times 2 to the 0 power. And I need you to know that 2 to the 0 is 1, not 0. So that does give you negative 3 times 1, which is negative 3. Let's double 2 more times here. Negative 12 doubled is negative 24, as these stay negative, and negative 24 doubled is negative 48. So there are your first 5 terms. What else did we find? The common ratio right here. We need the explicit and recursive formulas. You know, I started off your recursive formula right here with a sub 1. Oh, wait a second. We don't need the explicit formula. We're given it. I started the recursive formula out here with this a sub 1 right there. Ooh, that's going to be confusing, R and R. This R is for common ratio. This R is for recursive formula. Remember, you have to mention what the first term is in a recursive formula to find the value of the next term. You take the value of the term before it. And what do you think we do here? If the explicit formula for an arithmetic sequence says take the value of the term before it and add your common difference, here we're going to multiply our common ratio. So instead of an R here, of course, I'm going to be placing 2. So the reason we have to state a sub 1, however, is because to say, what are we doubling from? Just like I said for common differences, clearly it's not 0. And clearly here it's not 0. You can't be doubling 0 over and over. And clearly it's not 1 either. You got to say where you're starting from when you double. So what did we find? We found all that. We need to find the 8th term still. So we could have done that first. A sub 8, substituting it into that formula there. It's negative 3 times 2 to the 8 minus 1, 7th power. Now I know 2 to the 7th is 128. And negative 3 times 128 is negative 384. So the 8th term is negative 384. You will see me go to the calculator a couple times, and I also probably need to make mention of some specific things with regard to the calculator in and of itself. Okay, what I wanted to mention was with regard to rounding or use of fractions or all that stuff. We won't round, by the way. Okay, so number 6, a sub n equals 32 times 1/2 to the n minus 1 power. Before I move forward, I want to make mention of, you notice they put parentheses around this 1/2 here. Now that is a requirement. Not always. You notice even when I wrote the formula, I didn't put parentheses around it here. It's not always a requirement, but it is with fractions. And it is with negatives. We will be dealing with negatives on these. I made mention of that before. It wasn't a requirement here for this 2, because only 2 is the only portion of the base here. 1/2 has a 1 and a 2. With a negative, the negative should be a part of the base. It's the thing that needs to raise to the power. Order of operations states anything within parentheses applies. We need to make sure that this division happens within that raised to exponent. So that whenever you're writing something, you're required to put parentheses around fractions and negatives for your bases of these. All right, that common ratio, though, is 1/2, which means when you multiply something by 1/2, you're dividing by 2. You're dividing by 2, but it does mean there's exponential decay. It means there's exponential decay. So these values will shrink from positive 32 to start. Let's start from that. List the first 5 terms. Starting from 32, let's take half of that. Divided by 2, you get 16. Half of that is 8. And then 4. And then 2. Those are the first 5 terms. Now, the 8th term, by the way, the 8th term isn't far out. And the main reason I wanted to just say the 8th term is so that you are not getting numbers too outlandishly big or too outlandishly small. But please keep in mind that when I'm asking you for it, I want you to use the explicit formula, to try it. That's what's requested. Obviously, it's only 3 away from this number, 3 away from this number. You could probably find it pretty easily recursively. But if you're just going to keep doing that, then I'll change it to the 30th term, and I'll say do it now. Definitely want to practice the explicit formula work when we do it. So common ratio, first 5 terms. We need the 8th term. I'll use the explicit formula for it right here, which is a sub 8 equals 32. And this is where I get to speak on what's going to happen here. 1/2 to the 8 minus 1 power is the 7th power. Now, because this was presented in fraction form, it's asked for the most part that you keep your answers as fractions moving forward. So doing 1/2 to the 7th power, if your calculator is just going to give you a decimal by typing the 1/2 there, then think about what is 1 to the 7th power, what is 2 to the 7th power. You can do those in the calculator if you need to. Now, we already know 2 to the 7th power is 128. So 1 to the 7th power is 1, and then this is all over 128. Excuse me. This is all over. Let me try that again. 32 times 1 to the 7th over 2 to the 7th. 1 over 128. Which means 32 is dividing by 128. And this is where, you play fraction reduction. And I'm going to be doing the same thing with or without a calculator. I think this is 1/4. I think they can both divide by 32, and you get 1/4. So a sub 8 is 1/4 there. All right. I still need the recursive formula here. So the recursive formula would have been the value, to find the value of the nth term, you take the value of the term before it, and you multiply by your common ratio, which is 1/2. Probably good to put parentheses there as well to not get too involved there. Starting from your first term, which was 32. Okay, and that is number 6. All right, number 7, very similar, only you're given the recursive form instead of the explicit form. So let's move to there. Given this recursive form, find the common ratio, first 5 terms, 8th terms, and the explicit formula. So we start with the common ratio. Now, in that recursive form, find the value of some term, take the value of the term before it, multiply by -3. Heck, I would use parentheses around it. The R is -3, so common ratio. And we're starting, by the way, from -1. Let's start from -1. Let's write the first 5 terms. -1. What is that times -3? Well, it's a positive 3. 3 times -3, I'm sorry, this should say negative, times -3, -9. So you're going to notice here, you're going to get this oscillation of sign. I mentioned this before. In a geometric sequence, the signs either stay the same the whole time or they change every time because you're multiplying, by a positive or negative there. Times -3 is positive 27. Times -3 is -81. They're the first 5 terms. If they're not changing signs, something went wrong. Okay, so that's the first 5 terms. Now we still got to find the 8th term, and in order to do that, I should probably do the explicit formula. I do realize it's only 3 away from here, but those numbers are getting pretty big pretty fast. It's going to be somewhere in the 2000s, I think. And I'll let the calculator play with this a little bit. I don't know what 3 to some powers are, so I'm going to play with the calculator on this one. So the explicit formula should be, to find the value of some term n, you take the value of the first term. Oh, excuse me. I should actually say what the value of the first term is. You take the value of the first term, -1, and you multiply by your common ratio, n minus 1 times. You notice how I use parentheses around that 1 for the -3. That's very important for it. So there's the explicit rule for this one right here. And let's go ahead and use this to find the value of the 8th term. A sub 8 is going to be -1 times -3 to the 7th power. Again, I don't know what -3 to the 7th power is. I'm going to go ahead and go to my calculator. Now, the one thing that you're going to have to do here, I have my calculator right here. One thing you're going to have to do here is make sure that that -3 is wrapped around parentheses, because if 2,187 is negative, -1 times -2187. You need to make sure that when you do this in a calculator, you either wrap it around parentheses or you understand the mathematical rule behind raising a negative number to odd powers versus even powers. When you raise a negative number to an odd power, you get a negative result. Your calculator would treat it as negative if you don't put parentheses around it, but if you raise it to an even power, it should turn positive. And if your calculator keeps it negative, that's because you didn't use parentheses. Granted, we're about to multiply it by -1, so this becomes positive 2,187. So the 8th term is 2187. Now let's see if that makes sense regarding sign. I trust the number. Let's see if the sign does make sense. First term was positive. Negative. Second term was positive. Third term was negative. Then positive, negative. That's the 5th term. 6, 7, 8. Okay, the eighth term is positive. Every even term in this sequence is positive. The eighth term, I know we raised to the seventh power. That's because that's how many times you multiplied by -3. But the eighth term is positive, so we're in agreement on that. Okay, that worked out. And I think that's all we needed. Number 8, we have recursive rule right here. Starting from 1/2, we're going to multiply by 4. So 4 being that common ratio, r. Let's do this. 1/2 times 4. Well, it's the same as 4 times 1/2, or 4 divided by 2. So that's 2, right? 4 halves. And then the rest that we multiply by 4 should be pretty straightforward. 2 times 4 is 8. 8 times 4 is 32. 32 times 4, I think we just saw this number was 128. So those are your first 5 terms. To get the to get the eighth term, we need the explicit formula. So let's attack that one. To find the value of the nth term, we take the value of the first term, which is 1/2, and we multiply by 4. I use parentheses anyway. Multiply by 4, at least with a fraction. Multiply by 4 n minus 1 times. And then the eighth term. The eighth term is 1/2 times 4 to the 7th power. I don't know 4 to the 7th power. Give me a moment. 4 to the... Is that the same as 2 to the 14th? Which I don't also know. 4 to the 7th power is, 16. So it's 1/2 of 16,384. Can I do that one in my head? 8,192 divided by 2. 8192. So a sub 8 is 8,192. Again, if you multiply by 4 3 more times from here, we'd get there. Just working on some things, making sure you know how your explicit formula works. All right, that's number 7 and 8. Let's go on to this next page here, where we are going to do 4 problems very similar to that of the arithmetic sequence, such and such. This time you're given the sequence. We need to find the common ratio, the term named in the problem, the 10th term, the 9th term, the 12th term, the 12th term, the explicit formula, recursive formula, and 3 terms in the sequence after the last one given. So a few things to do here. Let's move forward. Clearly looks like we're multiplying by 4 each time here. So when it comes to common ratio, we can say r is 4. Now if I multiply by 4 again, 3 more times here, 64 times 4 is 256. Times 4 is 1,024. Times 4 is 4,096. Okay, those are the next 3 terms. 3 terms in the sequence. Okay, we found the common ratio also. Check, check. Explicit formula. The explicit formula will be a sub n equals value. The first term is 1 times the common ratio of 4 to the n minus 1 power. Yeah, it looks like I just used parentheses anyway. I got to think on that if I use a dot, but my instinct, my nature was just to do that right there, so trust it. Recursive formula. To find the value of term n, take the value of the term before it and multiply by 4, with your a sub 1 being 1. And then we need the value of the 10th term here. So a sub 10, I'm going back to my, 7 terms, only 3 terms away. I'm going back to my explicit formula here. A sub 10 is 1, the value of the first term, so just you can ignore it, times 4 to the 9th power, 10 minus 1. 4 to the 9th power, I have no idea, is 262,144. Yep, they went there. And I think that's it. All right, number 10. Now, number 10, you can see that oscillating sign thing. We're getting a pretty good indication of having a negative common ratio. And with that times 4 seeming to appear again, it's actually times -4. So your common ratio here is -4. Hey, I've seen these numbers before, but I never did this one times -4. 128 times -4 is 520, 512. -512. Times -4 again is positive 2,048. Times -4, I might use a calculator for this one. I don't want to mess it up. 2,048, times 4. Oh, 8,192, that's right. Negative 8,192. Okay, those are the next 3 terms there. Let's do recursive formula first, because I'm going to use a sub 9 for the next thing. which is really just 2 terms away. Why am I not doing times 4 each time there? I don't know. But the recursive formula, I'll start with that because I'm not really giving use to it anymore. We just did what we were supposed to do for recursive formula. A sub n minus 1 times negative 4. Notice my parentheses there. And then a sub 1, by the way, was, hey, negative 2. All right, there's that. The explicit form of this one here is a sub n equals, starting from the first term, negative 2, or multiplying by negative 4 n minus 1 times. And let's show that in a sub 9. A sub 9 is negative 2 times negative 4 raised to the 9 minus 1 is 8th power. Now, this is an instance where you definitely need either parentheses around the negative 4 when you raise it to the 8th, or knowledge that that should give you a positive result. Not the final answer, but the negative 4 to the 8th power. So I'm just going to do 4 to the 8th power. I know I have a phone calculator, and I don't trust the parentheses on these. 4 to the 8th. 6. Oh, this was this number. 65536. So negative 2 times positive 65536. Don't let that part be negative. And then this answer finally will be negative, or ultimately. So times negative 2 is 131072. Which I guess would have been this times negative 4 times negative 4. Now, wait a second. Oh, I'm sorry, negative. Did I say? I forget if I said positive or negative. That's negative. So this was the 7th term. The 8th term would be positive, and the 9th term here would be negative. There you go. Let's make that purple like the previous problem there. 2 more of this variety. Let's start dabbling in fraction territory. Let's see how we can do with that. Another oscillating sign as well. 3, negative 1, 1/3, negative 1/9. Again, it's not what you're dividing by. You might use that to first make sense of what you are multiplying by. But, so, to say we're dividing by negative 3 isn't enough because your common ratio is a negative 3. Right? If you're dividing by negative 3, you're multiplying by, negative 1/3. If you're not sure, again, how do you find your common ratio? We already know it's geometric, so we already know it's a common ratio. How do you do it? Take one number divided by the one before it. What is negative 1 divided by 3? That's it. Negative 1/3. Don't put a decimal. Don't work anything out. This is what we're multiplying by. So if we want to find the next 3 terms, we multiply by negative 1/3. That means the sign changes to positive. 1 times 1 is 1. And over 9 times 3 is 27. So 1/27. Times negative 1/3 is negative 1 over 81. That's 27 times 3. And then times negative 1/3 is a positive 1 over 243. So those are your next 3 terms in that sequence as we divide by negative 3, but multiply by negative 1/3. There's that. The recursive formula, a sub n is a sub n minus 1 times negative 1/3. I'm sorry, I was thinking of a word. In my previous video, I was trying to say the thing in the beginning of where I'm going to record a bunch of videos, and I said a smattening. I meant a smattering. A smattering, that's the word. The first term here is 3. 3 right there. So we're going to have that. The explicit rule, value of the first term is 3 times negative 1/3 to the n minus 1 power. So let's find a sub 12. This is one where I would probably definitely prefer to use this one. I know we're still 4 away, but and I'm keeping the number small enough to work this thing out. Now, this is one where, once again, we have to really pay attention that we're using fractions, so let's keep our answer as fractions. So a sub 12 is 3 times negative 1/3 to the 12 minus 1 power to the 11th power. So here's the ordeal. What I'm going to do in my calculator is I'm going to do, this is raised to an odd number. So this part's going to end up being negative. 1 to the 11th is 1. That part's fine, right? So this is 3 times negative 1 over, and I'm going to do 3 to the 11th power on there. Should be a pretty big number. 3 to the 11th. 177,147. So, it becomes negative 3 over this thing. But, this can reduce as well, right? You can divide both of these by 3, because clearly this came from 3. So divide both these by 3, and it's 1 over 59049. So this is negative 1 over 59049. Again, we're not putting the decimal of that. What is the decimal? 0.0. Look at this. Give me a second. I'm going to brighten my screen. Here's the decimal. And I'm sure... Hold on. Sorry, I have to hide myself. There's the decimal. And we're not going to round to like the nearest tenth there. And I'm sure that decimal is not ending there. I'm not positive, but maybe the decimal is not even ending there. So we're not doing the decimal of that, right? We have to get the fraction. There are times where just the fraction is the must on a problem like that. And that's one of them. So negative 1 over 59,049. Whoops. All right. Last one, number 12. Not the last one of these. After this, we're going to talk about arithmetic means and geometric means. So number 12 right here, we have negative 5, negative 10 thirds, negative 29ths, negative 40 over 27. You know, it's still pretty easy to figure out what you're multiplying by in these cases because you can really separate top from bottom. And because these fractions never reduced. It's weird when the fractions start reducing as you're going along and doing it, which isn't always very common, but it does happen. For instance, negative 5 times 2 is negative 10, and 1 times 3 is 3. You know, is this 2/3? Obviously, it's got to be 2/3 each time because it is geometric, but see that 10 times 2 is 20, 20 times 2 is 40, 3 times 3 is 9, times 3 is 27. So really, I mean, look, the common ratio is 2/3, and it is positive. Even though these are negative, the ratio is positive, right? So we're multiplying by 2/3 again. The answers will stay negative. So let's just do this. Figure out 40 times 2 and 27 times 3. So 40 times 2 is 80. 27 times 3 is 81. Hold on. I'm going to pause this for hiccups here. Okay, let's see if that one chug will work. Now, I was just going to mention, I did say fraction reduction could happen. You know, if it happens, it really only probably happens once because you're multiplying by the same thing over and over. Why would me multiplying more 2's on top and more 3's on bottom lead to any other fraction reduction thereafter? Right? If this thing is just multiplying more 2's, why would 2/3 cancel themselves out a little more each time? They wouldn't. So if anything, it would only reduce a fraction at most probably once through multiplication, through geometric sequences. So I probably misspoke a little there. So we're not looking to reduce anything here if nothing could be reduced since before that, which it couldn't. So negative 80 times 2 is, or 80 times 2 is 160. 81 times 3 is 243. And then one more here, negative 320 over 729. So that is those, you know, times 2/3 over and over there. All right, recursive, common ratio. Recursive formula here is a sub n equals a sub n minus 1 times that positive 2/3, as that was our common ratio, and starting from an a sub 1 of negative 5. The explicit rule, oh, I didn't box this before. The explicit rule was, or is, a sub n equals, first term is negative 5 times this 2/3 fraction raised to the n minus 1 power. And that's it. And a sub 12, this should be fun. There's nothing to reduce fraction-wise. We already know that. We can understand through what we have here. If 5 can't reduce with multiplying by 2/3, then 5 can't reduce with any powers of 2/3. So there's good news with that, right? So a sub 12 is negative 5 times 2/3 to the 11th power. 2/3 being positive there will give me a positive portion. Obviously, the answer is going to be negative, ultimately, though, right? So I'm going to do 2 to the 11th power. Oh, whoops, I did 2 divided by 11. 2 to the 11th power. Oh, I know that. That's 2048. So let's see, negative 5 times 2048 over 3 to the 11th. Did we do that here? 177147. That was on this previous problem here. So we got to do negative 5 times 2048, basically. I need that one on top. So times 5, sorry about this, is negative, well, not sorry, you'd have to do the same thing if you're working on this. Negative 10,240 over 177147. And again, it can't reduce. Because it's 5 times 2 times 2 times 2 times 2, whatever, over 3 times 3. Nothing can cancel there. Nothing can reduce. That's the answer. What is this as a decimal? It's not pretty. Once again, it's not a pretty decimal. We're not writing this as decimals, and we are definitely not rounding. Sorry, my screen's a little dimmer there. But we are not writing as decimals, and we are not rounding there. So just keep that in mind. Okay, that's a lot of the geometric sequence stuff as we referred to. The last bits that I'm going to do here is with regard to what are called arithmetic means and geometric means. Now, it doesn't say that here. It says find the missing term or terms. Now, this isn't going to be by guess and check, trial and error. I'm sure you could land on them sometimes, or we could make them extremely difficult for you. An arithmetic mean and geometric mean are named as such because they are with respect to averages within their field. So in arithmetic sequences, they have a common difference. So if you're finding a missing term between two numbers, you really want to average those two numbers, right? That's what arithmetic mean would actually mean there. I'm going to do it in kind of a different format, though, just so you're aware. In a geometric mean, it's not the average of these two numbers in a common difference kind of way. It's a multiplicative average. It's something that you actually find in similar triangles. I do know I have a video that covers geometric mean in a different way, but I'm still going to do something there different as well, so it really helps you on these problems right here. Let's start with the arithmetic sequence stuff. Here's the idea. It is an arithmetic sequence. They tell you that. So arithmetic sequence has a common difference. I have some term in a sequence. It's not necessarily the start of the sequence. It doesn't matter where it is. But there is one term in the middle of these two terms in the sequence. If I am at 10.1 and I'm going to add some common difference here, I get this value. If I take that value and recursively add a common difference one more time, I get this value right here. That means that if I take 10.1 and I add my common difference twice, I get 5.1. Or 10.1 plus 2d equals 5.1. This is an algebra problem. Subtract 10.1 from both sides, you get 2d equals negative 5. Divide both sides by 2, you get d equals negative 5 halves. Or in this case, because it's decimal form, negative 2.5. So I'll go and give you the decimal form of that. Is that my answer? No, that is the common difference. So I need to find out what is 10.1 minus 2.5. That's what's going to get me my number, and that number is 7.6. So that ends up being your term there. So that is, that was averaging your numbers. 7.6 is 10.1 plus 5.1 divided by 2. That is one other way to do it, but that's only for a single arithmetic sequence. If you have multiple, for a single arithmetic mean. If you have multiple arithmetic means within, it's probably best to kind of go with a different result to that, which is what I just did before. Let's try that one again with this thing. How many times do you have to add a common difference from 25 to negative 5? 1, 2, 3, 4, 5. There are 5 of them there. This is really the best way for me to approach it with you guys. I wouldn't think of any other way, to be honest. 4 spaces in between, 5 apart, whatever. So 25 plus 5d equals negative 5. This might not be a clean number either, right? The whole goal of this is I don't want to necessarily make this the easiest thing possible. Maybe it is, maybe it isn't. Subtract, actually maybe this one is. Subtract 25 from both sides, you get 5d equals negative 30. Divide both sides by 5, you get d equals negative 6. So what's happening here is recursively, guys, let's go ahead and just subtract 6 over and over again right here. And we get, let's see if this works, 19, 13, that was a good year. 7, 1, and yes, negative 5. So filling in the terms from the common difference there of d. And that's arithmetic mean. Geometric mean is not through a common difference, but from a common ratio. So there's an idea of proportionality I can show you afterward, but that's just for a single term that's missing in between here, not so much for one of these. Geometric means a little bit different in a couple ways. For starters, again, through multiplication, we're multiplying by some r to get here and some r to get here. That means that negative 4 times r is negative 80. Or that's negative 4r squared is negative 80. So this one is through, we're going to solve by using roots, not by division. Well, there's one division right here. Not through a subtraction and division, but by division and roots here. We're going to use a square root here after we divide by negative 4. So r squared equals, if we divide both sides by negative 4, we get r squared equals positive 20. And then we take the square root of both sides to solve this. Now here's the other part of this that's really interesting about geometric means. I'll show you in a sec. R equals, now the square root of 20 I'm going to simplify this. I'm going to use not decimals, right? I don't want an irrational whatever number. It is irrational, but I don't want to decimal. The square root of 4 times square root of 5 is 2 root 5. So the answer here is 2 root 5. You got to be careful. When you take the square root of a variable there, you're going to be left with a plus or minus. And this is the tricky part about this problem. It's the plus or minus portion. I mean, it should be fine if you know your algebra and solving quadratics, specifically when it comes to something being squared. But the tricky part about geometric sequences that you really got to be sure of and understand is that, remember, the signs can change. You don't know whether this number in between, by the way, these aren't the answers, this is the ratio, but we don't know whether this number in between is supposed to be a positive number or a negative number, because we can change sign. Yes, this could be negative, 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 but if you had a common ratio that was negative, it would be negative, positive, negative. So this actually then could change sign in between. That's why the plus or minus exists here, and we're going to multiply negative 4 by positive or negative 2 root 5. As long as you put the plus or minus here, you're good. So what is 4 times 2 root 5? That's 8 root 5. And apparently, 8 root 5 times 2 root 5 would be 80. Now, the plus or minus is taken care of with that. So there's a plus or minus there. Are they always pluses or minuses? Depends on the number of terms. So not necessarily. But in this case, yes, positive, negative, because one space in between. It'll take care of itself based on whether you have something squared or cubed or whatever. And remember, you can take the cube root of a negative and get a negative. All right, so let's go to this next one here. Last one, number 16, where we have 2. And then we're going to multiply by r how many times? Once, twice, 3 times, 4 times, 5 times. So 2r to the 5th equals 6,250. If I divide both sides by 2, I get r to the 5th equals 3,125. What is it? I think that's 5. And you take the 5th root of both sides there, you get r equals 5. And do I put plus or minus 5? Well, no. When I take an even root of a positive number, it's plus or minus. When I take an odd root of a positive number, I get a positive. An odd root of a negative is a negative. Think about it. If it was plus or minus 5, like let's assume it could have been negative 5. What would we have? A positive number here, then a negative, then a positive, then a negative, then a positive, then a negative. 6,250 wasn't negative. This sign is going to tell you whether this was going to be positive or negative to begin with. So it's only positive. So we're multiplying by 5 each time, right? 2 times 5, times 5, times 5. So now we're just going to multiply by 5 and figure out all these numbers in between. So this is going to be 10, 50, 250, and 1,250. And yes, that should give you 6,250 afterward. Okay. And I think that's it. So that ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for watching geometric sequences and some things involving arithmetic sequences and means as well. Take care. I'll see you the next one when we start talking about series, arithmetic, and geometric. Bye.